All right, so to continue with the theory, now we're going to discuss solutions of higher order homogeneous linear equations. And I'm going to do this primarily based on second order equations, and then we will mention that the results can be extended to linear equations of any order. Okay, so let's consider the second order linear homogeneous ODE. In general, it will look like a2 of x y double prime plus a1 of x y prime plus a0 of x y equal to 0. And eventually what I would like to do, I would like to figure out how to produce a general solution of this homogeneous equation. And before we get to the general solution, let's figure out some properties of these type of equations. And so the item number one is going to be this. Let's take, suppose that we have two solutions of this equation, so that y1 and y2 are solutions of this equation, which I'm going to label as star. So they are solutions of star. That is, both y1 and y2 satisfy the equation. So a2 of x y1 prime plus a1 of x y, so y1 double prime, y1 prime plus a0 of x y1, that is equal to 0. And the same thing for y2. So if I take this equation and copy it and label y as y2, so y2 also makes this equation an identity. All right, so now I'm going to consider a function y of x equal to c1 y1 of x plus c2 y2 of x, where these coefficients c1 and c2 are arbitrary constants. So I have two functions, y1 and y2, and out of them I construct a third function, which is c1 y1 plus c2 y2. We're going to say that y is a linear combination of y1 and y2. So a linear combination of two functions is going to be a function which is equal to c1 times the first function plus c2 times the second function. That's a definition of a linear combination, which, as we will see shortly, can be extended to more functions. Okay, so whatever, this is my y of x. How about we do this? Let's take the derivative of y of x and the derivative of c1 y1 plus, I'm actually going to quit writing x, just remember that all y's are functions of x. So y prime is going to be c1 y1 plus c2 y2 prime. Well, derivative of the sum is a sum of derivatives, and derivative of the constant times the function is constant times derivative of the function. So this is c1 y1 prime plus c2 y2 prime. And then nothing prevents me from computing y double prime. What is y double prime? That's y prime prime. Y prime I just computed. It is c1 y1 prime plus c2 y2 prime. I'm taking the derivative of that. And this will give me c1 y1 double prime plus c2 y2 double prime. Nothing too fancy here. Okay, so with this in mind, now let's go back to our equation star. And what I'm going to try to do, I'm going to compute what the left-hand side of this equation is going to be if I plug in my y of x into that left-hand side. So a2 of x, again, I'm not writing x's, but I'm assuming that everything here depends on x, a2 y double prime plus a1 y prime plus a0 y. What is that? So it's a2, y double prime is c1 y1 double prime plus c2 y2 double prime plus a1 c1 y1 prime plus c2 y2 prime, right? Because y prime is written here, and plus a3 plus a0 times y, and y is c1 y1 plus c2 y2. Okay, whatever. Now I'm going to distribute all a's. a2 c1 y1 double prime plus a2 c2 y2 double prime plus a1 c1 y1 prime plus a1 c2 y2 prime, and then distribute a0 plus a0 c1 y1 plus a0 c2 y2. So I got all of those terms. Now I can try to combine them, and I'll combine them in the following way. So there is one term with c1, another term with c1, third term with c1. Then there is a term with c2, c2 here, another c2 here. So out of the things that are underlined once, I can factor out c1 to get a2 y1 double prime plus a1 y1 prime plus a0 y1. And out of the remaining terms that are underlined twice, I can factor out c2 to get a2 y2 double prime plus a1 y2 prime plus a0 y2, like that. But then I know that y1 is a solution of my ODE star, so that means that the left-hand side of this is equal to 0. And that's the same thing that I see in the first parenthesis. So that first parenthesis, the whole thing is going to be 0. And y2 also is a solution, so the left-hand side of this equation is equal to 0. And the left-hand side of that equation is precisely what I see in the parenthesis here. So that means that this is also 0. So what we get is C1 times 0 plus C2 times 0 equal to 0. And so the conclusion is that this particular y equal to C1 y1 plus C2 y2 satisfies the equation a2y double prime plus a1 y prime plus a0 y equal to 0. And so therefore the conclusion that from all of this that we are going to make is this. If y1 and y2 solve the equation star, then any linear combination of y1 and y2 also solves the equation star. So this is called a superposition principle. Let me give you an example. So let's consider the second order linear ODE. Let's say y double prime plus 2y, let's make it 4y, equal to 0. So what I'm going to try to do, I'm going to try to verify that y1 equal to sine of 2x and y2 equal to cosine of 2x, that these guys are solutions of, let's label this with a sharp, are solutions of this equation. How do I verify this? I need to compute second derivatives. So y1 prime is going to be cosine 2x. y2 prime is going to be minus, well, I have to use a chain rule, so I'm missing 2 here. So 2 cosine of 2x minus 2 sine of 2x. Then y1 double prime is minus 4 sine of 2x. Each time I take a derivative, another 2 comes out. And y2 double prime is going to be minus 4 cosine of 2x. And so then if I take y1 double prime plus 4y, What is that? y1 double prime is minus 4 sine 2x plus 4, y1 is sine of 2x, and that is 0. So y1 is a solution. And y2 double prime plus 4y2 is equal to minus 4 cosine of 2x, right? That's my y2 double prime, plus y2, which is plus 4y2, which is 4 cosine 2x. So that is equal to 0. Okay, and so then from this, if I use superposition principle, it follows that y equal to c1 cosine 2x plus c2 sine 2x that this function solves my equation for any combination of C1 and C2. Okay, so why is this interesting in any way? Well, if I look at this thing that is circled here, then what do I see? I see that y is a solution of my ODE. So this y is a solution, and it contains two undetermined parameters, C1 and C2. So y is a two-parameter family of solutions to the second order equation sharp. And therefore, if it is a two-parameter family of solutions of a second order equation, right, I expect that the second order equation will have a general solution which contains two unknown constants. This already is a solution of my equation which contains two unknown constants. So therefore, y equal to c1 cosine of 2x plus c2 sine of 2x. I expect that this is a general solution of my equation. And when I'm solving an ODE, what I want to find is a general solution. So in this case, I'm done. So on this example, based on this example, we can make the following conclusion. That to find the general solution of the second order ODE, it is enough to find two solutions and then form the their linear combination. So that means that in order to find the general solution of a given second-order linear ODE, the only thing that I need to do, I need to actually find two solutions, and out of the two solutions, then I can construct a general solution. The superposition principle then is a very powerful thing because it allows you to reduce the task of finding infinitely many solutions to just finding two solutions. All right, so let's do a couple more examples to illustrate these ideas. Y double prime plus minus y is equals 0. That is again a second order linear ODE. What I want to show that y1 of x equal to e to the minus x and y2 of x equal to e to the x are solutions of this equation. So that's number one, and number two, I want to find the general solution. And basically I have to repeat the same sort of computation I just did in the previous example. For part 1, y1 prime for e to the minus x, when I take a derivative, chain rule says that minus 1 will come down, so that y2 prime, double prime, y1 double prime, minus comes out again, so this is e to the minus x. Y2 prime, y2 is just a regular exponential, so all derivatives of the regular exponential are going to be equal to the exponential itself. So everything is equal to e to the x. And then if I take y1 double prime minus y1, I'll have e to the minus x for y1 double prime. E to the minus x is y1 itself, so that is 0. And for the function y2, second derivative is equal to the function itself, e to the x minus e to the x, that is 0 again. And then I have two functions, two solutions of my ODE, so then I can find the general solution as a linear combination of these two functions. So y is c1 e to the minus x plus c2 e to the x. Okay, and now let's try to repeat the same example, but in a slightly different setting. So I want to consider exactly the same equation, but now instead of two functions that I considered before, let me suppose that y1 of x is 2 e to the x, and I want to repeat the same calculation. So y2 is still a solution because I didn't change y2 and I didn't change my equation. How about y1? So if I take twice e to the x and I take a derivative, I'm going to get twice e to the x. If I take a derivative for the second time, and again, 2 just comes out, and derivative of e to the x is itself, so again, 2e to the x. So then y1 double prime minus y1 is going to be 2e to the x minus 2e to the x, and of course that is still equals 0. And so now I have two solutions of my ODE, and I can form, it seems that I can form a general solution, so it would be C1 times 2e to the x plus C2 e to the x, and that looks like my general solution. Unfortunately, if you look at this carefully, you will see that probably not. This is probably not a general solution. Why it is not a general solution? Because I can take e to the x and pull it out. It's a common factor. And then inside, I will get 2c1 plus c2 times e to the x. Well, what is c1? c1 is an arbitrary constant. What is c2? c2 is an arbitrary constant. So then 2c1 plus c2 is an arbitrary constant. So this is basically nothing but c e to the x. And if I write c e to the x, then if I look at this, this is a parameter family of solution, but it's a one parameter family, because the fact that I have two parameters is bogus here, because I can combine those two parameters into one. So this would be a one parameter family of solutions. And so therefore it is not a general solution, because a general solution is supposed to have two parameters entering. So now let's examine, so what is the problem here? What's the difference between the two examples? So in example number 1, I have two functions, e to the minus x and e to the x. In example number 2, I have functions e to the x and 2e to the x. So in the example 2, y2 is a constant multiple of y1. Right? And then if that is the case, then the linear combination of y1 and y2 is still a constant multiple of y1, which means that, again, I really only have one function from a point of view of constructing a linear combination. So the conclusion from that is that this is a situation I want to avoid. I don't want one solution to be a constant multiple of another solution, because in that case, I really cannot construct a general solution. So therefore, just like I said, to construct a general solution, should have y2 that is not a constant multiple of y1. Okay, so in the example 1, e to the x and e to the minus x, e to the minus x is not a constant times e to the x, so that's a good pair to construct the general solution. In a second case, e to the x and 2e to the x, 2e to the x is a constant multiple of e to the x, so that's not a good pair to construct the general solution. Let's introduce some terminology. If y2 is a constant multiple of y1, then y1 and y2 we would say are linearly dependent. Otherwise, y1 and y2 are going to be linearly independent. Okay? So then, based on our examples so far, e to the x and 2e to the x, these guys are linearly dependent. E to the x and e to the minus x are linearly independent. And so, going back to what we were talking about before, so to find the general solution of a second order ODE, I have to have two solutions and then form their linear combination. This would only work if one solution is not a constant multiple of another. So what I actually need is that two solutions are linearly independent. So we have to modify this statement. Let's copy it and modify it appropriately. So to find the general solution of the second order E or the ODE, it is enough to find not just two solutions, but two linearly independent solutions of the ODE and then form their linear combination. So let's massage this to a linearly independent solutions of that ODE. And then form their linear combination. All right, so that is something that we're going to pursue later on when we're going to try to solve particular second order equations. So at this point, it should be clear that if I want to solve a second order linear homogeneous equation, what I need to do is to find two linearly independent solutions of that equation, because then out of those, I should be able to construct a general solution. And we're going to finish this lecture by considering the case of the nth order ODE. So now to generalize this, this to nth, order ODEs. I'm not going to prove anything or show similar computations like I did for the second order equation. But basically everything that we have done for the second order equation should be true for nth order equations. So if I have my nth order ODE, let me copy it so I don't have to write it down again. So given, and again, we're talking about homogeneous equations. So given this nth order linear homogeneous equation, I have to replace the right-hand side by 0. In fact, let's get rid of given. So I have my nth order ODE. Superposition principle still holds. You can verify. So superposition principle holds in the same way as before if I have any number of solutions, y1, etc., yk. So maybe I have 15th order ODE and I have 3 solutions, y1, y2, and y3. Solve this equation. Then a linear combination y equal to c1 y1 plus etc. plus ck yk, then this linear combination also solves the same equation. Okay. You can again verify it simply by substituting. All right. So then, if we want to find the general solution, okay, let me, before I write something about general solution, let's talk about it. If I want to find the general solution of this ODE, what would I need to do? General solution should contain n parameters because the highest order of a derivative here is n. So to solve this equation, I'll have to integrate n times, and the outcome will involve n unknown constants. My general solution has to depend on n constants. And so then, if I want to produce a general solution, I should know n solutions of this ODE, and I can form a linear combination of n solutions, and will have n unknown constants. So in that way, just like in two-dimensional case, in the case of second-order equations, I should be able to produce a general solution. But similar to what happened to second-order equations, I have to make sure that I cannot express one solution of my ODE in terms of other solutions. So for example, let's look at the following example. So let's suppose that I have y1 equal to x, y2 equal to sine square of x, y3 equal to cosine square of x, and y4 equal to 1. Okay? And I'm going to form a linear combination of these. A linear combination will look like this. Y is c1x plus c2 sine square of x plus c3 cosine square of x plus c4 times 1, and that's my linear combination. So it involves 4 unknown constants. So this involves 4 generic constants. Okay, so, but however, what do I know? I know that 1 is equal to sine square of x plus cosine square of x, right? And so then I can write my y of x in the following way. So y is going to be c1x plus c2 sine square of x plus c3 cosine square of x plus c4 sine square of x plus cosine square of x. Fine. Then I can distribute c4, and I'll have c2 sine square of x plus c4 sine square of x. So this is c1x plus c2 plus c4 sine square of x. And then I have c3, and c4 also multiply cosine square of x, so c3 plus c4 cosine square of x. And now again, just like before, c2 is a known constant, is arbitrary constant, c4 is an arbitrary constant. So c2 plus c4 itself is an arbitrary constant. I can call that c2 bar. And this I can call c3 bar, because that is also an arbitrary constant. So overall, c1x plus c2 bar sine square of x plus c3 bar cosine square of x. So really, in this case, there are only 3 unknown constants. So then if, for example, I'm solving the 4-Fodor equation, 4-Fodor ODE, and somehow I know that those 4 are 4 solutions of my ODE, and I form what I think is a general solution, and then in a general solution, actually, I don't have 4 unknown constants, but only 3. So with 3 constants, the thing is not a general solution. So what I have to make sure is this. In this case, what I had here was a problem. It was a problem that I could have taken 1, and I can express 1 as a sum of our 2 solutions. Sum of 2 solutions is a linear combination of sine square and cosine square with coefficients 1. So if I can express one solution as a linear combination of some other solutions, then the constant in front of that solution will just be distributed between other solutions, and that constant is going to be irrelevant. And so then we can generalize a notion of linear independence to the function, not just 2 functions, but n functions. So a definition. If I have functions y1, etc., yk, these functions are linearly dependent if one of these functions can be written as a linear combination of some other functions from this list. And if this is not true, if I cannot express any function as a linear combination of other functions, so otherwise this set of functions y1 through yk is, or the functions are, linearly independent. So then, for example, if I pick the same set of functions as in my previous example, then we have already shown that one can be written as a linear combination of sine square and cosine square. So then this set of functions is linearly dependent. Dependent because y4 is equal to y2 plus y3. Example number 2, if I have y1 equal to x, y2 equal to x squared, y3 equal to x cubed, then clearly I cannot write x cubed as a linear combination of x and x squared, and so therefore these functions are linearly independent. Okay, and so the last statement that I'm going to make in this lecture, so therefore, to find the general solution of the nth order linear homogeneous equation, which I'm going to copy now. Where is it? What I need to do is I need to find n linearly independent solutions of this equation, and then form their linear combination. Okay, so just like in the case of a second order equation, it would be enough to find and linearly independent solutions, and then you form a linear combination and you found the general solution. So in the next lecture, then we're going to figure out a systematic way of checking whether the solutions of your equation are linearly independent, and then we will discuss a little bit solutions to non-homogeneous equations, but that's next time.